the disruption. The Clay Christensen's talk from last year, on Innovator's Dilemma, and telling their story. But I think it's very illustrative of what our thesis is, which is power and energy efficiency is really one of the big problems that the industry's facing.
Yeah.
And our approach to that is we believe different computer architectures that are maybe not intuitive to program right now are going to be leading solutions over time, just because that's the only way we're going to get to exascale and solve some of these larger problems, and on a more frequent basis. So not only are the problems getting bigger and exascale needed, but the number of people who need teraflop level computing is growing.
Bigger problems, a bigger market.
Yeah,
and
exactly.
then you have the missing middle too. So more people coming in on the low end and the high end.
Yes, exactly right. Exactly right. And oftentimes I was talking to someone at Intel last week about the missing middle problem, and this group of energy companies that are, this woman was focused on the energy sector specifically, that are all workstation based, but they're now being kind of pushed or pulled, I don't know which way, to stay competitive into more cluster based traditional high performance computing. And where do they go? For the support, the technology, the infrastructure, and so forth.
Right.
So we're really targeting our offering at addressing that emerging space.
Can you give me a few sentences, the basics of your company?
Yeah, we're basically a cloud-based infrastructure operator. So we host and provision what I would call accelerator-based platforms. So GPU and FPGA, and that's in future. Intel Mic, DSP. I mean,
who's your hardware partner?
We are
announced with Convey yesterday.
On the FPGA side, and then on the GPU side, we're actually, our initial SKUs are Supermicro based, 1U GPU. But we're also, we're in discussions with HP and others on the GPU SKUs that are available. For us right now, as a young company, we have two really offerings. One is more private hosted, so for people that say, look, I don't want to run on shared infrastructure, I just want to operate, I want you guys to manage and operate our cluster so we can run our jobs and run our software. And so that hardware is dedicated. It's more of a traditional hosted model, but it's just purpose-built and focused on high-performance computing, and specifically GPUs. I mean, there's nothing stopping us from doing just CPU only, but right now we are right now focused on a couple of different domains. The primary is, in order to really lift the FPGA cloud component and get that business up and running, is focused on bioinformatics. So all the genomics and sequence alignment. So you have this massive wave of sequencer deployments, the latest generation that's just cranking humongous amounts of data, and a lot of the organizations, small CROs, research organizations, the tier 1 guys, they're not provisioning enough compute to deal with their requirements or the amount of data they end up having already, the sequences are spit out that they need to process. So they have a backlog of data that needs to be processed. And so what we're really trying to bring to bear is, as opposed to doing with traditional big memory CPU only machines, look at the type of acceleration you can achieve in your performance throughput by using these FPGA accelerated platforms. And oh, by the way, you don't have to provision those in-house. You can run them as a service on demand. So, in that model, it's a traditional supercompute model where we're operating a shared facility and we are batch processing jobs on these accelerated platforms. So bioinformatics, I live in Houston. Our data center's in Dallas. So oil and gas is a space that's been a little slower to adopt cloud because, as Jensen talked about, you have this mainstream, that's kind of done it in-house for decades, and data sets are, extremely large and almost immobile, in terms of over the wire. Yet at the same time, all of them are trying to figure out, how do we deal with capacity crunch? How do we scale out and get more flops? We don't have either the data center space or the budgets or the CapEx to do that, so we've got to figure out what the cloud can offer. And so oil and gas is a segment we are porting with our GPU infrastructure, and that's a segment that's one of the first adopters of GPU technology for accelerated, improving their performance on their RTM codes and so forth. So
Okay, so you're going to say there's two.
Yeah, I would say so. The two sort of offerings, and then from a vertical perspective, bioinformatics is one of our key focus areas on FPGA computing in the cloud, and then with our more traditional parallel compute with GPUs, oil and gas, rendering, graphics. We have some people doing standard, more traditional computational algorithms, that are more just math, or they're accelerated math, like libraries in R and the statistical packages, MATLAB, and those are cut across a fairly broad set of either academic or across a lot of different verticals. So we obviously expect we serve a lot of verticals. Digital manufacturing simulation is a big segment right now that I think over time will start serving, but right now we're just as a startup.
What's your best estimate as a time frame for that to start taking off?
It's actually I think that
where do you think we are in that cycle?
I think we're in still early adoption from a cloud perspective. I think a lot of these guys are dealing with the same problems the oil and gas guys are, the finance guys, they built pretty big installations to do their simulation. I mean, Airbus is a great, I think you guys put that article out on Airbus.
Yeah, right, HPC-as-a-Service.
A great example of, you look at the numbers and you look at what performance requirements you have year on year on year, and there's a capacity crunch. And so think of us as we're basically bringing more compute capacity to these problems as a service type of option. And so for us, ours are the as-a-service is hosted, kind of private, and then what I would look at as more traditional batch. We've done a little bit of provisioning like an Amazon or Rackspace, where we'll do nodes as a service on demand like utility. But I think that there's some challenges with the whole virtualization side of it.
Extra layer, yeah.
In terms of affecting performance, efficiency, it doesn't solve our efficiency problem. And so, we think that these accelerator architectures and trying to democratize that with making it easier to access the technology. So if you want to
consume that, right?
Yeah. If you want to write code to run on an FPGA platform and accelerate it, the cost of entry is pretty significant. But as a cloud provider, if we can start to get more people access to those platforms, we want to democratize it so that we have more ingenuity going towards these unique architectures that then we can pipeline into the applications that service the data processors, right? The guys who ultimately care about the science or their data sets. So I understand that. I think that's one of the reasons we're trying to bring a different model than the virtualized x86 model, because when people, it's very exciting to think about this virtually infinite pool of resources, of cores that you can run your embarrassingly parallel applications on. But when you start to really look at what that adds up to in terms of provisioning, running, and teardown, it's not cheap. And there are some great use cases, but we think that a model that is more helping people to operate those infrastructures or scale their capacity through a provider like us that has good scalability. I mean, we're a data center company, so our whole goal is about giving more capacity. So a commercial company may have constraints around their data center size and so forth, and if they put it in-house, but we give them the next best alternative from a cost standpoint, which is, hey, as opposed to just scaling out these VMs, with potential performance degradation, we give you, it's just like in-house, but we're just your operations partner. Now, the second piece of that on the as-a-service HPC is the data processing play. Think of it as workload as a service, or a job as a service, where these guys are running resource managers and schedulers and scheduling their jobs, and all we're doing is giving them a web service to interact with, so there's no provisioning, no infrastructure headaches.
I was going to ask you about cluster management. Go ahead.
Yeah, I was going to say we abstract that problem on these heterogeneous architectures from the users. The guys in bioinformatics haven't been doing cluster computing for all that long, so for them, what they care about is, I got these two read sequences and I just need my SAM file, out. And if you make that run faster, spare us the details on how you do it, but if you can pipe that, make that easy to use, and I only pay for when I'm processing, that's where we answer that question of the cost model. And there's always going to be a little premium, right, for an as-a-service. It's an ease of use, quicker turnaround. So users have to judge how they use that capacity. If everyone had their best option, they would provision it in-house. They build it. It's cheaper to do it in-house, but there's a reason semiconductor manufacturers are fabless semiconductor companies, because you got to go invest $1 billion to build a wafer fab. And so the same kind of thing for supercomputing. As the scale gets bigger, the investment hurdle rate is higher, so it's better for a player to be able to amortize that across a lot of customers, just like TSMC does for silicon. So that's I think one of the ways we address that. We expect to actually start to profile some use cases against what I would call like the commodity cloud versus our accelerated cloud, where we can do kind of like-for-like power consumption, runtime, and dollars, and then do some comparisons, because right now that's still kind of ambiguous. That's a challenge. I mean, there's no question. I did a talk last week about cloud deployment models, the 3 different cloud deployment models, and from a HPC perspective.
Okay.
And I really break it into 3 models. There's infrastructure as a service, so think of Amazon and Rackspace and those guys, which is your building blocks are VMs. It's almost like you still got to do all the headaches you do if you're building it in-house, but you're just building it virtually. Then there's the platform guys like Cycle, RightScale, the guys that do some process automation around that, so instant one-click clusters. So they take care of all the API stuff, but it's on Amazon. Same framework. You just get to choose if I want someone to do some of the building for me, or if I want to do it myself. And then the third model is what I call HPC-as-a-Service, or you could actually bucketize it as SaaS, software as a service, because you're running the apps. And that's where I would put guys like R Systems, Nimbix, Sable Core, SGI, IBM, COD, guys that you're running on bare metal. You oftentimes have a low latency network interconnect, high performance file systems, and you're doing batch processing, just like a national lab or an academic supercomputing. And our belief is that model is kind of where we're orienting ourselves that way. And keeping people close to bare metal. It's not to say we might, as virtualization gets better and the abstraction for GPUs gets better, there's a path for us to do more of an Amazon.
It's lower on the stack then.
Yeah.
It's lower,
Yeah, we're
closer. A lot of people are moving up the stack.
We're getting people, keeping people close to the hardware, because we're focused on the efficiency problem. We've talked to people about Hadoop, and big data problems, and that's getting more, HPC-ish, with all the talk about big data. But, I'm not convinced that solving a text mapping problem in a 900-node cloud cluster on Amazon and operating that is potentially a better solution than partitioning that problem into 4 FPGA servers that can crunch it in a quarter of the time with running 4 nodes in a data center versus 900. You know what I mean? And that's just a hypothetical, but it's those kinds of challenges that I think we're trying to help people turn the problem on its head and figure out, is there a faster, more efficient, better way architecturally to solve it. And I think that one of the concepts that we're really trying to drive towards is the sense of appliance-based computing. The sense of, if you had an unlimited amount of resources, you would probably build a purpose-built appliance to solve a common problem the same way over and over and do it ultra efficiently. And when we talk about mobile phones being optimized and packet processors went from into dedicated silicon, that if we could do that, we would, but the economics haven't justified that type of approach. But our feeling is that FPGA technology start to actually put problems in silicon that now it looks like a purpose-built application appliance. It's a purpose-built supercomputer for one application. It does it better than anything else you could throw at it. You could take a parallel problem and actually take it from an n-node cluster and drive it to a single node, co-processing architecture. So then if you take that thought, and then you imagine a cloud provider that has FPGAs are reprogrammable, and you put it into a workflow that you can change the that appliance, for its purpose, real time or dynamically. That's what Nimbix really is bringing to bear. This concept of you could queue a bioinformatics workload, have a machine look like an ultra-tuned highest performance power operation costs for that app, and then your next workload is a Monte Carlo simulation that you now change the persona of that machine to be optimized for the next algorithm.
Does it require a high level of programming skill? Is that what are the pain points?
Yeah, so there's for us, the assumption is that these applications have already been invested in and optimized and tuned, and then we run those as a service. So there's still a lot of people that are trying to figure out, how do I put my problem in an FPGA to get 100x speed up and for less power. So the challenge there is there's a very high hurdle for investment in tuning the apps because it's a tough programming model, right? It's not like you're writing CUDA code or x86 code. You're having to profile your code, look for areas to optimize, and then understand how that fits into silicon, and then converting that to circuits. So there's another step in the tool chain that makes it harder to do. But our thesis is that the tools are getting smarter. We're getting better. You could have GPUs starting to figure out how to actually optimize your tool chain for programming models on alternative architectures. But ideas, those are getting better and smarter, which means we can take more legacy code and get lower cost to port that into these architectures. At the same time, Nimbix is democratizing the cost of adoption of that technology, and the goal is more apps running on these architectures that improve by orders of magnitude run times and energy costs. So for us,
what is the energy cost of the FPGA?
So the energy, if you look at kind of performance per watt based on, and it's going to depend on the application. There's some applications that an FPGA, if you're looking for raw flops, potentially your performance in double precision, your performance per watt, there's going to be challenges there, but when you can put an entire data streaming problem, or something that has to have almost low latency data in and operations performed on that and data out, that breaks kind of traditional parallel programming models. FPGAs become uniquely suited for driving the performance. So graph problems, alignment, obviously, genomics, where you're doing kind of search and mapping, data sets. FPGAs are gonna be almost the fastest thing you can do, short of building an ASIC, to implement those problems. So but performance per watt, if you take, for example, a traditional bioinformatics application, CPU, big memory, and you start to look at the run times and operating costs, it's really about ROI or a TCO over the number of jobs you're running on the machines. And FPGAs will generally beat in terms of cost and power consumption over the productivity of that substantially. And we're still quantifying some of those in real numbers for, and publishing that data. So we expect to be more active as we have more applications really benchmarked that will continue to roll out that data. So. Rensselaer Polytechnic Institute is one of ours. We have a rendering company that out of Paris that's it's basically video rendering on GPUs. We have heavy, I guess, on the graphics side because our first deployments were GPUs, so a lot of interest on the kind of real-time ray tracing. And then we're in beta right now with some bioinformatics companies that they're not announced yet, that we're looking to adopt the FPGA processing platform. And then we have one oil and gas company that we're getting ready to launch a beta trial on the GPU side. It's a tough thing. I mean, it's a noisy space, and there's a lot of big players, entrenched players like Amazon making more noise. IBM is obviously, HP announced a cloud offering, which is still kind of unclear how that'll take shape. But Our biggest differentiator is focused on, call them accelerators, call them co-processing architectures. I mean, and if you look at the big, the Intels, right? They pretty much said, okay, we're doing Mike. It's a co-processor architecture, because there's an understanding that as we hit the power wall, we can't get the performance just on CPU-only architecture. The supercomputing community has basically said that with the GPUs when China last year took that #1 spot. We believe that validates our approach to heterogeneous computing. And then the second thing is, with respect to cloud service, we believe that the economics of that missing middle are what favor where we kind of come in to. We're not going to be the ultra performance within the latest InfiniBand and all the Uber tech, but this emerging technology that we can take down market into that space that really allows people to do their science and focus on their development and innovation, as opposed to learning how to do HPC and figuring out all the challenges and making those investments. So we feel pretty good about it. We closed on a round of funding in early fall, and venture, and as well as there's a group called Blackwell Energy Group in Dallas.
It's in the press.
Yeah, it's Silver Creek Ventures and
Blackwell and Silver Creek, or that's
yes, those
Blackwell Energy, Silver Creek, and then
Techwell. Yeah, sure. And so then we're obviously continuing our fundraising efforts, just because it's an infrastructure play for us. We got to go off and provision, expensive gear and operate data centers. So
front-end cost too.
But I think that's just a great validation of the investor community, really starting to understand where there's been a bit of retrenchment in some cases with venture and HPC because of times in the past where things just didn't quite happen, and it was viewed as a niche. And I think the investor community is starting to realize this is getting much bigger than a niche. It's kind of going mainstream, and then you add in the whole big data Web 2.0 challenge, and these things, how they converge, is still very much an opportunity, a market opportunity that I think people see.